Hello everyone, today we're going to look at a single proportion mean using the normal distribution to find what's called a confidence interval. The mean of a sample, which we denote by x bar, is called a point estimate because it uses a single value, or a point, to estimate the population parameter, which in this case is mu, the population mean. This chapter focuses on confidence intervals, which uses an interval or a range of values to estimate mu. Each confidence interval is associated with a confidence level, which is some percentage. Typically, you'll see 90%, 95%, 99%, so it's usually a high percentage. It tells us how confident we are that mu is actually in the interval. So remember, we don't typically know what mu is. If we did, we wouldn't have to estimate it by a sample. So we're fairly confident that mu is in some given interval. Each interval looks like x bar plus or minus what the book calls the EBM. The EBM is the error bound for the mean, sometimes just called the error. So x bar plus or minus the EBM is the interval that starts with x bar minus EBM and goes up to x bar plus the EBM. So it's always an interval that's centered around x bar, which again was our point estimate. The confidence level is the percentage of confidence intervals. So confidence intervals we typically abbreviate CI. So the confidence level is the percentage of confidence intervals that contain mu when repeated samples are taken. So each confidence interval is associated with an x bar, which remember is the mean of the sample. And if I keep doing this, I keep taking repeated samples, I'm going to find repeated x bars. And then for each x bar, we calculate the confidence interval. And if I do that enough times, then whatever my confidence level is, say 95%, 95% of those confidence intervals will contain mu. Alpha is 1 minus the confidence level. So if the confidence level is 95%, then alpha would be 5%. If the confidence level is 90%, then alpha will be 10%. And alpha is the opposite of the confidence level, so it's the probability that our confidence interval does not contain mu. And we know that we can use the central limit theorem if we have certain stipulations that are guaranteed for us. So if we know sigma and our n is large enough, or our underlying population is already normally distributed, we can use the central limit theorem to help us find the confidence interval. We start by finding z sub alpha over 2. So we want our two tails area to be alpha. So by definition, in each tail, we want it to be alpha over 2 because we know it's going to be symmetric. So we're looking for z sub alpha over 2. And because of symmetry, we're going to have z sub alpha over 2 and negative z sub alpha over 2, right? Because again, it's symmetric about the mean. And if we're looking at z's, the standard normal distribution, it's centered at 0. So our goal is to find plus or minus z sub alpha over 2. And then our EBM, our error bound, is actually z sub alpha over 2 times sigma over the square root of n. So we're taking our z-score from our standard normal distribution, and then we're kind of unstandardizing it by multiplying it by the sigma for our sample distribution of the means. And remember, that is sigma divided by the square root of n. So again, we take our z sub alpha over 2 and multiply it by sigma over root n because we're using the central limit theorem. So this is going to be the main part of this section. So we'll do an example. Find a 90% confidence interval for the following information. X bar is 4.5, sigma is 2, and n is 36. So alpha is going to be 1 minus 0.9. Remember, 90% confidence interval. So alpha is 0.10. What we're interested in is alpha over 2, so we're looking at 0.1 divided by 2, which is 0.05. To find z sub 0.05, you can either use Excel or the table, the standard normal table. So I would suggest using Excel. So I want you to pause this and open up Excel and use the commands to make sure you're getting the same z value that I'm getting here. So I really want you to play along with this, as it were. So you should be getting 1.645. So I'm going to plug it into our equation here, which again, remember, is x bar plus or minus that error bound. So x bar is 4.5, z sub alpha over 2 is 1.645, sigma is 2, n is 36. So then I'm going to simplify this side because order of operations, the multiplication and division, come before the addition and subtraction. And using a calculator, we get 4.5 plus or minus 0.548. You always want to go to more decimals than what the mean is given as. So the mean has 0.1, one decimal place. So I would go to at least 2 or 3 for the error bound. And then what I'm going to do is I'm going to turn this into the actual range of values. So I'll do 4.5 minus 0.548 and 4.5 plus 0.548. And we get the interval 3.952 to 5.048. Okay, so that's what our answers are going to end up being, an interval, so a range of values. And what this means is that I am 90% confident that the true mean, so mu, the true population mean, is somewhere between 3.952 and 5.048. So let's try another example. Suppose that average pizza delivery times are normally distributed, with sigma being 6 minutes. A random sample of 28 pizza delivery restaurants is taken, and a sample mean delivery time was found to be 36 minutes. Find a 99% confidence interval for mu, the true mean delivery time for all pizza restaurants. So our n isn't actually high enough. Remember, we would need 30 in order to use the central limit theorem. But we're supposing that the underlying distribution is already normally distributed, so that n being greater than or equal to 30 doesn't come into play here. So the first thing we need to find is z sub alpha over 2. So alpha is 0.01, and again that's 1 minus the confidence interval, the confidence level, which was 0.99. So 1 minus 0.99 is 0.01. And we want alpha over 2. So we're looking for z sub 0.005. So 0.01 divided by 2 is 0.005. And again, I suggest, if you haven't already, to take out Excel or the table and look up this number for yourself and make sure you can get the same values. So you should be getting 2.567. So again, we're going to plug it into our equation. Our x bar is the 36, our z sub alpha over 2 is the 2.576, sigma is 6, n is 28. Again, we combine these guys first because of order of operations. So I get 36 plus or minus 2.921. Again, I'm going to go to at least a couple of decimal places for the error bound. So we are 99% confident that mu, the true mean delivery time for all pizza restaurants, is between 33.079 and 38.931 minutes. So the 33.079 is the 36 minus 2.921, and the 38.931 is the 36 plus 2.921. So this 3 should be a 2. I don't know, I just typed that in wrong. Right, so it should be 38.921 if I did the addition correctly. What happens if I want a 90% confidence interval instead? So my alpha would be 0.10, just like it was in a previous example, and alpha divided by 2 would be 0.05. So I'm interested in z sub 0.05, which again is 1.645. So the only thing that's changing is my z sub alpha over 2. Right? My x bar is the same, my sigma is the same, my n is the same. So when I plug that in with my new z sub alpha over 2, I get 36 plus or minus 1.865. And then if I do the addition and subtraction, I get the interval 34.135 to 37.865. So if we notice, this interval is smaller than the previous one, but we're also less confident in our answer. And that's always going to be the case with confidence intervals. The higher the confidence level, so the more confident we are, the larger the confidence interval has to be to accommodate that. Okay, so if an 80% confidence interval is going to be smaller than a 90% confidence interval, which is going to be smaller than a 99% confidence interval. And remember, they're all centered around x bar. So each confidence interval is contained inside the previous one. So let's try another example. Heights for 10-year-old females are normally distributed with sigma equaling 2 inches. Find an 80% confidence interval for the true mean height of all female 10-year-olds. If we took a sample of 20 10-year-old females and found x bar was 53.65 inches. So again, the underlying distribution, heights for 10-year-old females, is normally distributed, so it's okay that our sample is smaller than 30. Our confidence level is 80%, so our alpha is 20% or 0.2. Alpha over 2 is 10% or 0.1. So we're looking for z sub 0.1, and if I use Excel, I get 1.282. So remember, 80% is not a terribly high confidence interval as far as confidence intervals go. So our interval itself will be fairly small because we're only 80% sure that it's inside this interval. So our z sub 0.1 is smaller than it was for the 90% and the 99% confidence intervals. So it's only 1.282. So we're going to plug it into our equation. So x bar is 53.65 plus or minus z sub alpha over 2 is the 1.282. Sigma is 2. N is 20. Again, we will combine these guys together. We have 53.65 plus or minus 0.573. So if I do out that addition and subtraction, I can say that we are 80% confident that the true mean height for 10-year-old females is somewhere between 52.368 and 54.932 inches. Okay. So again, we are a range of values versus the point estimate of our x bar. And as our last example, we have the mean age of a group of 50 students at NEIT was found to be 23.4 years. If sigma is 8 years, find a 95% confidence interval for the true mean age of all NEIT students. So the first thing we have to do is find alpha. So if the confidence level is 95%, then alpha is 5% or 0.05. So alpha over 2 is 0.025. And z sub 0.025 is 1.96. And again, this is coming from Excel, or you'll get close to it if you use the table. So I'll plug it into my equation. So I'll have 23.4 plus or minus 1.96 times 8 over the square root of 50. If I simplify the right-hand part of that, I'll have 23.4 plus or minus 2.217. And then I'll do out the addition and the subtraction to get my range of values. And this will give me that I am 95% confident that the true population mean for all NEIT student ages is somewhere between 21.183 and 25.617 years. Okay, so again, we're taking our z sub alpha over 2, kind of unstandardizing it, so multiplying it by our new standard deviation, which is sigma over root n, because we're using the central limit theorem. That's our error bound, so we're going to add it to the mean, and we're going to subtract it from the mean, and that's going to give us our range. Okay, so let me know if you have any questions, but read through the book, and good luck.